Okay, it's recording. And so it first mentions the the diffusion is optimizing for this loss function, which is error matching, and then it says that for diffusion model, if we think about the t is going to goes into infinity, uh, like there is a way to connect this error matching with score matching, and the score, yeah. So basically, what we have. So their first attempt is that assuming that we have this period distribution, and they can like take any point there, and if you take any data space, any data point in the data space, it will be a very low likelihood point. It's very close to zero. So the question is, how do we, if we randomly sample in the data space, how do we transform that into a likelihood position? They mentioned the method called stochastic gradient lengthening dynamics, where that if they start at a random position with very low likelihood, like a Gaussian, then we can follow this schedule, which is just lengthening dynamics formulation where you increase your likelihood by keep doing this kind of step. And then they are saying that there is one issue is that we actually do not have this period, and we cannot have the score. So the way to solve this is that even if we don't know this period, we can maybe we can go just get the score of this probability, and we call it score function. And given that score function, if we can have access to this score function, then we are able to just sample from this Langevin dynamics. And yeah, yeah. And then they have some visualization. So they claim that they want to fit a model to the score function. So the loss function they are considering is basically something like this. So we have our model to estimate the score at point X, and then we want to match it with the actual score with the p data. And the problem of this is that the p data, if we are like approximated with a huge data set, then that is totally non-differentiable because p data is a delta function of all the data samples in the data set. And so the way they do this is that they add a little amount of noise. They add a little amount of noise to any data samples. So n is a data index, and they add a small amount of noise. And so if your original data set is it's lots of Dirac delta, then what you have is that lots of Dirac delta add some small amount of noise and becomes a mixture of Gaussian. Yeah, so the Q data distribution of Xn is basically the likelihood of all of them, like all of the data samples, with a Gaussian added to it. And yeah, and then like this score function is tractable under this under this new formulation. Just simply by adding a noise, they are able to directly calculate this score of p data. And
What is the reason that it becomes from? Oh, never mind. There's already a 1/2. I was going to ask what 1/2. There's already a 1/2 in equation 3.
Okay. Yeah, and then yeah, and then I think they can just like calculate the distribution of calculate this analytically by formulating it as here. So basically, if we are adding, so basically here, what it's saying is that we take the score like through this Gaussian would become the like error scaled by this the Gaussian error you are adding, which is unit Gaussian, which divided by the actual STD of the error. And then yeah, so we can directly have access to the true score of the of the data point. Then the loss function we can just have the loss function by training with a score matching. So we can for any x x that we want to train, we just want to our trained score model to match the actual score at that point. Yeah, the actual score is parameters by this, which is derived before. And then this basically, if you look at this, the loss function here, it's extremely close to the original diffusion loss function here. It's just here you are modeling the error, and below it's modeling the score, and they are all trying to match the parameterized error or score with the actual error you are modeling. And then it mentions score matching training and generation things. So in training, basically what you do is that you pick a data and you sample epsilon, and then you train the noisy version of the data, which is a mixture of Gaussian, and then you can calculate the score at that data point, and then you can calculate the gradient with respect. You can just so this is just SGD, which is just to optimize the loss function trained with score matching. And then yeah, and then in the generation process, what we do is just we go through the Langevin dynamics, where we use the trend score to update our data sample from noise to the data one step by one step.
The whole point of Felix DDI and DDPM objective was that the data is extremely sparse in the high-dimensional space, so you do not have values for your score function far away from.
Oh yeah, yeah.
So how does this solve it?
Here it didn't. So in this block, it didn't say it solved that problem.
The problem is still there. It mentions it right at the end of that.
Yeah, yeah. So it's mentions here how to connect the score matching and diffusion based models. So the difference between the two equations above, so this equation that the sigma here is fixed. So that mixture of Gaussian is defined to be a fixed distribution. And
Diffusion will make more assumption.
yeah. So to make it to be equivalent with diffusion, this needs to be a function of t.
Yeah.
Yeah. So it mentions that like to turn the score matching to be a diffusion, it needs three things, which is that the sigma needs to be a schedule, which is a function of t. So the t, so basically through the Hall-Langevin dynamic process, each step you should define a different sigma t. So at different time step, you are assuming you are adding different amount of noise, and that would solve the sparsity issue in the data space. And yeah, and the second is trivial, is that you give the variance schedule to the model so that the model knows, your parameterized model knows how much noise is should it remove. And the third is yeah, we modify the objective to be aware of this schedule. So basically, based on the different schedule, sigma t, the objective is weighted by the is weighted by some lambda t. So, for example, if your
It's
variance,
a single model.
Huh?
S theta is a single model.
oh yeah,
Prediction,
it's a single model that can denoise different amount of noise. Yeah. And the lambda t is just the weighting of the of the error during training. And then I think what's left is just to give a coding example for this.
Is this shown to work empirically better than BDPM?
No, this is before all that. This is just Anil Landry dynamics.
Yes, this is not better than DDPM. DDPM is better at that point. And then later they formalized the more general framework and then did it better than DDPM. Yeah, that's the next block.
So basically, for the score matching stuff, I like the future would have like various standard deviation from t, for example, from 0 to 1000. It only like takes one step from pure noise to general.
No, only consistency models. do that. So here it's like at any t, you go back to zero. Your denoiser tries to denoise to zero because you cannot really denoise from t to t minus one, right? So that's why it's modified so that you go from some xt to zero. Sorry, x zero, which assuming x zero is zero.
Well, here sigma t is, so if you scroll down a little bit, but in the schedule, sigma t is increasing from 0 to 1.
Yeah.
And Anil Landry dynamics is first using larger step sizes.
That you can tune, right?
Well, here is
So Anil Landry dynamics is first using larger step sizes, so that if you start from low probability places, you go. Yeah, right. So isn't that corresponding to larger sigma in like? Oh, you're going from t to 0.
this is generation.
Yeah. Okay. So in training you increase sigma with t, and then in generation your sigma effectively.
It's two. There's two different things. In training also you try to do the same thing. Yeah, it's just that there's two processes involved. One is the doing Langevin, what exactly the same. If it's Langevin or doing equals iteration. So one of them takes you from the true probability to the distribution to the true noise, and the other part, reverse part, takes you from noise to the distribution.
Yeah.
So during training, it's the same thing. It's like both you're trying to do the same.
Yeah.
Which is that when you define a loss function, you do some sort of KL divergence between the forward path and the reverse path.
Like
So
consistency
both have to do
and
that. Both are like if you're in the noise distribution, the sigma is larger. As you get closer to your sample, to your P of x, your true P of x, the set size becomes smaller. So that's regardless of training.
I see. I think I have one. So one question here is that this Q data here xn yeah, it's a GMM with like so here this xn tilde is one data. It's
Noisy version of xn, where the noise was epsilon. That's how Q data became Gaussian.
so it's calculating the likelihood it's being like the sum of all of the likelihoods of all of the Gaussians added together. Right?
Yes,
Yeah.
yes.
So it can be calculated for any data points, right?
Yeah.
So this could just it doesn't need to be xn tilde. It can just be any x, right?
Yeah.
And then but this is kind of like conditional score matching, right? Because it's only matching the this is only matching the score of the conditional score. Is it true?
No, because anyway, when we're averaging, you will average over n, right? So it doesn't matter.
I think this is because of linearity. Like L of theta is expectation over all data samples, right? But I think they're pulling the expectation outside the integral.
Yeah, so inside, when you're matching the score, you're matching it for each data point. So it doesn't matter, right? Like, so,
Oh, so it's matching through all of the data sets.
yeah.
Oh, I see.
It's like you can swap expectation.
I see. But then in its training, so during training, it's training from the x tilde you get is by like sampling from the Gaussian, right?
Yeah.
Yeah.
I see.
This accent tilde is also excellent.
Yeah, just x tilde. But why is it only trained on like the GMM distribution? So this x tilde, it's so through this it's basically like sampling. So inside this is basically sampling from the GMM, right? And why is it purposely by sampling from the GMM and only train on those positions? Can it do on other?
Because we want a closed form expression for the score, right? That's why we went with this. Like, I mean, you can decide what, because we don't know P data, right? So it's kind of like we are defining that distribution with Q data. So I don't know if I understand the question.
Yeah, what's your question? The same thing, right? Because how is this core model learning far away from the data? It's the same question. Is that your question?
Yeah, so I'm saying that during training, I'm optimizing this data for any lots of different x tilde, right? And I need to sample this x tilde and then evaluate this, and then train it. And then here, I think the x tilde is done by sampling from the GMM. It formulates by this amount of sigma.
Wait, no, it's not. No, right?
It is.
No, you have your GMM is your Q data.
Yeah.
But your x tildes are you start from
Data.
and then you denoise it. X tilde is your denoising process. In your denoising process.
But we're training.
No. X
Yeah.
tilde is noised.
Tilde is sampled from a Gaussian near the data.
Yeah, but not from the GMM Q data.
No, not from the data.
Yeah.
So you pick one data point and then you It is technically, it is from the Q of Q itself, because you pick that data point uniform.
But you have multiple steps of sample, like noisy file
Wait, right? Confused, in training or doing inference?
during training.
There's no step concept here.
There's no step, it's just you're learning the score function at that point, there's no step.
This is different than the actual score. Score matching is during training. Right?
Score matching, you directly learn the score function instead of approximating it with some MMC.
Actually, I think if we learn as to the forget about question number 4. If we try to learn x theta x tilde on q data x, q data xn directly, then we think about one more objective where you want to directly model s theta x tilde to the score function of q data that GMM. I think then if you sample from q data xn, right? Then the expectation with respect to q data xn instead of the conditional here. So what I'm saying is, these two are, I think, related by some constant.
Yeah,
It's not exact, right? It's not exact, right?
L theta, yeah, I don't think so, because that's what it's linearity. I think you're putting that summation. Technically, you should have that summation at summation delta ln n of x given x all of x, right?
Yeah, you need to have this inside, right?
Yeah, sigma should be inside, but I think because of linearity, we will do that.
It's squared. Why would that be linear?
Oh, it's this one.
Oh,
No, the
that's-
expectation is linear, right? Like if you scroll up, they have that expression for P data, right? You're just, this
This.
one, that one. No, that one.
This?
No,
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 that's-
L
Sorry, three,
data
number three.
with P data, right?
So
So,
it's essentially expectation over Q data of X, and then you break the 1 over X, like sum over all samples out.
So we should
you have the
sub.
normal
So we
inside.
should. Oh, I see.
That's why there's some linearity.
So we should substitute all of those p with this q,
Yeah.
right?
That,
Yeah,
yes, yes.
But then I think what the so
and then you will take the summation out and the integration will go in. So if
And
you
then you have this here.
substitute
I know.
Q data there, right?
Oh,
That
that
There-
makes
there
sense.
is- There's the summation inside, right?
Yeah, yeah,
That's what-
yeah.
that's what- that
Yes.
gets out,
So
that gets
this
taken out.
so this should be put inside, right?
That'll come outside when you take this.
Yeah, but when they derive the score, they you can even the score can be interchanged, right? Like now you need to do differentiation with respect to the Q data, right? But there's a summation. The summation can be taken out. So that's why the derivative is with respect to only ln of the distribution, not and then you will have a summation, which
See the summation not only on the inside the square term, it's also in the E of x data term, like just before dx.
yeah.
So there's two summations there. That's why it gets taken.
So this should match the gradient of log of this, right?
Right.
Yeah, and outside also there should also here also there should be a summation, right? I think somehow that takes a thing. Here also there'll be a summation.
But that's here.
Oh yeah,
that's
so for
there.
both.
That's fine. Yeah, that
That-
can be taken out.
That is taken out, but this cannot be taken out, right?
So I'm saying that's why I think there should be equivalence in terms of plus some constant.
Yeah, there'll be some.
Some constant will be there. It's not exact.
But that's not parameterized by theta, so it does not matter, right?
It is parameters. Theta has to
But-
take account
But
at
the
least
S theta should actually match the
Yeah,
score of
exactly.
this.
Yeah.
That's true.
But it's only using this one point. It's only using one data point, right?
I think we should just go through that paper there and see.
No, I mean, like I have seen the derivation when they start from Q data xn, they actually try to model S theta to match Q data, the GMM, and they do some steps, and then finally they show that it can be written like this.
Yeah, so we have to just check the derivative.
So basically, I'm saying it's the same loss function plus some constant. So constant doesn't matter.
I see. I
So
see.
that's why you match this. And the main advantage of it is that
Easy
the
to
conditional is inside, right? That's
Yeah.
why
Easy to compare.
the down score function becomes very easily calculable.
Yeah, you sample from here and then inside is
Yeah,
tractable.
and yeah, you can do it for each sample, yeah.
I see. I see.
I think we should just look at the derivation. They're given like three
What's the this thing?
Yeah.
No, this.
Three. So
No,
there's
I
three.
think the citation, right? Hyberman.
So this.
No, actually, that is also I read the paper. That paper they don't talk about this one. Actually, this is not exactly score matching. It's denoising score matching.
Yeah.
So Hybernian talks about score matching, and he has a different expression. And Vincent Vincent had a paper on denoising autoencoder. And denoising autoencoder is similar, right? It kind of gives a noisy data and then tries to give x tilde and predicts x. And then he wrote another paper saying that there is some relationship between score matching and denoising autoencoder that is called denoising score matching. That is exactly this one. Question number 4.
Okay.
So basically he put everything here because denoising score matching is actually what inside diffusion, right? That expression. But actually Hybernian wrote it for EVM.
What?
Yeah, so he tried to model one unconditional density and all, and then his expression was different. But for this for denoising score matching, the main advantage is that you don't have to design the density. So if you're only concerned about sampling from the model, you just design the score. That is the main advantage. And if you
But I have a but what I'm thinking is that if
so if sigma is very small, q data x tilde is approximately equals to q p data, right?
yeah that I know. So the score of this is not tractable for any kinds of x. It's only tractable for xn. That is is it because like some of them are most of the n's are too far away if you sample from one thing?
Because this will log of sum, right? Calculate.
Yeah, the log. It's basically the log of sum.
Log of sum becomes
So that
log of the Gaussian.
that's why you cannot get rid of it, right?
No, they got rid of it, right?
So there should be the gradient of x and then the log of the summation of the lowing, right? The lowing, there should be a summation inside, right?
Yeah, that's you start from there. I think you can do some algebra and then you can arrive at this point.
Okay.
I think so.
Okay, I see.
Actually, there's a log sum inequality, right? That will work. I think this log.
But that's
of
an
the sum-
inequality.
I don't think these are equivalent. There has to be like this is the upper bound of.
Yeah. I don't think it cannot be equivalent. Log sum equality.
There's no log sum equality. It's log sum inequality because log of the sum is less than the sum of the logs. Always.
That's Jensen.
I mean,
Some-
yeah. But my point is that this is an upper bound.
So this is I see. So it's not purely analytical.
I mean, I think what they're saying is only the score for each Gaussian distribution is analytical. Because I don't think they're claiming for the GMM because then it doesn't make sense.
Yeah. Yeah, so even for score matching, it's still like
No, I think there may be a derivation that they arrive to L theta from this. They start from something. Then I think look at this Vincent 2011 paper. What is the paper?
That's the noising those things, right?
Uh-huh. That's the paper. Can you open it? Will it be there? The direction.
A connection between score matching and denoising. What? What's it?
From page, from page 6, it has already come to the equation 4. So,
Yeah, you're saying 3.2, go to
Yeah.
3.2. I
yes.
think that's where he's, yeah, see this, this is what you're talking about, right? Like he just adds a constant to it.
Yeah, yeah.
And now the log and the sum are swapped here.
Oh,
This is different.
why is what?
No, there
Why is
no,
that?
there is Jacobian term there. No, go back. Go below a little bit. Tell me Q functions somewhere.
Why is it expanded it out?
That 3.2 result is from original score matching paper. Go below. It should have some.
Why is there? Why it becomes?
See equation 7 and below.
Yeah, here they got a
Oh,
X
yeah,
to
here they use some noise. Exactly, right? This is the original of the objective, 7 and objectives. That's what you're talking about, right?
Yeah.
Q sigma. Q sigma, if I think if it is defined like this, then that's what you care about. It is so that 7 is equal to something else. Yeah, question 9.
What did it say?
This still assumes nothing about Q, right? Like for us, Q is a GMM, right?
Here it's also a GMM. Right?
Where is it?
The X tilde given X is just a Gaussian, right? It's not GMM. Q sigma X tilde is GMM. Make sure.
So Q of that's conditional.
Q can be any. I thought Q is just like a another distribution, like variational inference, right? Like Q can be anything except that it's going from X to X tilde.
No. I think for information they assume it to be Gaussian. So uh, it's a distribution over X tilde where mean is X and with some variance sigma square. That's why like number 10 becomes very simple because you put log and then exponential goes away.
That's just saying the conditional is a Gaussian.
Yeah. So that's what I'm saying. From
Conditional-
7 to 9. I don't know if see equation number 7 is the one we care about, right?
Yeah, he's
Yeah.
that, and what the hell is that? Like,
That's almost equal, I think. Equivalent or something.
yeah,
Did-
so
did-
he's
did
not
they
doing
say-
it.
So that's equivalence, however, breaks in the limit.
But that's ISM, right? Down, like how does he jump from unconditional to conditional? From Bayes?
It was derived with the what? Yes. It's in appendix.
It's now considered slightly that's inspired by both the score matching and by the
That's the proof for 11.
we define the noise from the underlying to the
No, we care about if 7 or 9 are equal. They are equivalent
no,
to
it's
7 or
not.
9.
It's not equal. They're just saying it's inspired.
But if you scroll up. No, scroll up. I thought it's 3 point. Yeah, it says it's
What?
no, go up a little. I think it's 3.2.
Why is 7 and 9 equivalent?
They
it's
are- they
written
shouldn't.
it should be, right? Like only X is I mean it's 9 is conditioned on X which you're averaging out. So why does it matter? In 9,
Yeah. What is averaging out?
so we now have conditional is between 7 and 9. The difference is it's q of x tilde given x here, right? So we're now conditioning on x.
Yeah.
But then if you take the expectation with x,
There's a square.
no, that's that there also.
How is 7 and 9 related?
Check the 2005 paper there. It's like
What?
go a bit out a little bit.
7 and 9 is just that's just a marginalization, right? Like if this is conditional and that's on x tilde. So if you take the expectation over the joint distribution of x and x tilde, then isn't 7 and 9 the same thing?
No, but the inside. But
Inside.
no, but the inside there's a square. That's the problem. Intuitively can think of marginalization of these things.
He has to get inside the norm trouble.
It's also like an upper bound system. So Tarzan window density estimate. Haifa window.
But we do this trick many times, right? Like even after this, when where inflows when we don't have like in the continuity of measure expression, we don't have p of xt, right? Then we just do conditioned on x zero.
Yeah.
See, it's the same thing, right? Like they're
But
also in the
this-
loss function, we just average over x zero and say it's, which is 9 here, which is like we're just
Yeah, they say it's equivalent.
yeah. So is it like a fundamental probability thing that we don't we haven't seen?
No, I think what they do is.
Because of
So
the
they
direct.
spun it out, the norm. Go to equation number 7. Yeah, spun it out. So there will be so what the log of score of that q sigma x squared is a constant term, right? So there, if you only take the terms corresponding to psi, there'll be a psi square term in norm, and there'll be inner product between these two.
Okay.
What they do is only one step they show is that inner product between these two are inner product between psi and then log of q sigma is equal to psi and also psi and the conditional, something like that.
So psi only with the conditional.
Yeah, plus some constant term. That's what they show.
But is that equal or like an assumption? Like, is there, like, I mean, as in like there are some other terms that we're just like not considering? Just how is that possible? The dot product, the inner product becomes a conditional norm? I can't see it.
They're doing assumption that lots of the samples are very far away or something. So they are orthogonal to gradient.
Actually, we have the derivation in the appendix. Scroll all the way down. Yeah, this one.
Oh,
Yeah, they're literally proving that 9 and 11 are same. or equivalent.
Also, they are the same.
Okay, so they start from. Wait. Go out.
Also, they got here. Go out. Go where?
No, I'm saying the first term they start from.
This is not. This is the unconditional score matching.
Yeah, but they S theta is the that term, right? S theta is the inner product term.
Yeah.
So they show that the inner product term is both above below. It's actually inner product over the, but only the expectation changes in the joint.
So it shows that there's only one conditional that pops up.
I'm saying. So finally again they complete a square plus and constant.
No, it makes sense. So
Oh.
since we have log of q, right, and we have a partial derivative, and then you have the expectation over q, so you can just like do stuff there to make it conditional, which is what they're doing.
Will you say that again?
So just scroll a little up. Like if you just follow this, right? Like look at the cross. So we have this inner product term which we need to reduce to a conditional, right? To
Yeah.
make it 11.
Yes.
So look at what they're doing. So the expectation is over q. So now you have a q that you multiply to each term in the inner product. But you also have log of q, which you are taking a derivative of, which is nothing but 1 by q times the derivative of q. So that way the q gets cancelled.
Oh, I see. I see. So everything left is just conditional.
Yeah, then you can marginalize q of x tilde as just like it is a marginalization of the joint distribution, right?
Oh, I see.
And then they pull the X out. So that the outside becomes a joint.
Hmm.
Yeah, makes sense. So it is not equal there. That's only the cross. That's only the product term.
Yeah, but then you can make it it's like completing a minus b whole square kind of thing. We have the a square term, we have the a b term, and then whatever we want.
So that part squared is okay. So that part is not related with theta, so it's just a constant.
Yeah. So the difference between 9 and 11 is they have some non-theta constants, which is in an optimization
I see, I
perspective, they are
see.
the same.
Yeah.
So they just change the last term to another term that is based on conditional square.
Yeah, they
And then they make
scale
another
this.
square.
Yeah, they scale the
Yes.
square term. Okay, so they are equivalent. Okay. And then the score matching loss is a perfect loss. So. The score matching loss is a perfect loss. Totally.
It's not like elbow or something.
Yeah.
We just we don't have the true score, we have the noisy score. Noisy fetch score.
But just a little bit noisy.
Yeah.
And where does the joint between x tilde and x go to? So previously in the previous paper we have outside there's an expectation of both x tilde, like joint between x tilde and x.
There is some, right?
That's
So-
just the sum, right? Because it's Gaussian. It's still there is Gaussian.
Because qxn is now the sum of deltas.
Yes. But what is the joint between x tilde and x?
Qxn times qx tilde then xn.
They're not independent.
No, they are not independent. I'm saying this is just a conditional probability.
Wait, which part?
Oh, I see. So it becomes a normal times qx. Qx is q data.
Yeah.
So next one is score-based generative models. They first have a review on the diffusion-based model. The so basically the basics of about diffusion and score matching. And then they talk about SDE and ODE. So for example, in the DDPM, the process, the forward process is defined based on this. So this delta is just equal to 1. And then they are saying that at each time different step, if they make that each step instead goes into a delta, then it becomes something like this. And then they talk about ODE and numerical methods. So they are saying that ODE is something in this form. So dt dxt is some function of xt and t. And through some initial conditions, you can just integrate to get xt. And fxtt is called a Fichte field. And then the way to solve this ODE is just by integrating, or you can discrete, you can use numerical methods to discretizing the integration. So it's like you write this
Regular.
yeah, just regular ODE. Yeah, so just a small, the difference in xt is the Fichte field multiplied by the delta. And you make this delta to be, for example, one step in the diffusion. So it could just be 1 in DDPM, for example. And then it's also possible to run from t equals to 1 to t equals to 0, just go through the other direction. And it's just connecting this generative model. So x0 to be data, x1 to be noise. So if we know this Fichte field, then we can run backward Euler's method to get a generative model. So now he moves into SDEs. So they are thinking of SDE as ODEs whose trajectories are random. And so with some like another term. So dxt is so dxt is determined by the fxt dt. They call it a drift term. And another, which is a diffusion term. So this dvt is a Gaussian distribution shifted by the uninormal shifted by a GT controlling the amount of noise.
So it's a random process where if you take two time instance, right, T1 and T2, so if the difference between them will be distributed as a Gaussian distribution, where the variance will be just the time difference between T2 and T2. I'm explaining stuff, but it's
Makes sense.
It would be something like this, right? So
it would be T2 minus sigma times T2 minus T1, that's what it would be, right? There will be a base sigma.
Oh, what?
The sigma's 2 square, right? That sigma is actually
And
V.
this is tau, right? Or
Oh,
2.
that's tau. Sorry, I have it was V.
So it's like for any tau.
Adding, like, Gaussian process.
Yeah, but this sigma tau will be based on tau. I'm
Oh,
sorry,
oh,
will be a
oh.
function of tau.
Yeah, yeah, yeah.
Yeah.
Oh no, it should be
Tau times sigma.
tau times sigma, right?
Yeah.
Tau times sigma squared.
Here, VT is the inner process, right?
Huh?
VT.
Yeah, VT is
So what is DVT?
DVT is means that this thing, which is just VT minus T minus delta T.
Right now, it's some small change.
So then DVT is some random variable with very small.
DVT is a Gaussian.
It's that Gaussian.
It's just this Gaussian. Tau sigma squared. It should be dt sigma squared, something like that. And oh yeah, it's having something here. Yeah, it's already here.
It's diffusion term.
So
But, here we're assuming at this point we know FNG, or we can create whatever we want.
Primarily to control the variance of some variance of
oh, they cannot, they have different versions. Some do not control, some control. They have it later.
I'm saying it's it is a deterministic function, right?
Yeah.
So ultimately it will contribute how much.
Oh yeah, 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 yeah.
That's why we have the variance exploding literally means GT will be like some sigma which increases with
Right.
GT is just a schedule.
Yes.
Yeah, so they are assumed to be known beforehand. So then the forward process is predetermined. And then so I think one property of this SDE is that given that SDE in this formation, they have a probabilistic ODE. They have a ODE whose solution follows the same distribution. So if they are all starting from the same, for example, XT distribution, and then you solve it, and you solve x0 by the above equation or by the below equation, the x0 are the same distribution. So instead, they are able to directly use this ODE for sampling. And so so I think people have derived these things somehow. And so directly estimating the score by score matching, you are able to sampling by this ODE. So no winner process anymore. And the drift and diffusion are still there. And there's a score function term here. Just derivation, and we take it for granted here. And then what they do is just they assume that x1, they design the process so that like the x1 would very closely to be a Gaussian, and then they sample x1 from a Gaussian distribution, and then run this probabilistic flow ODE. Use a numerical method to solve X0 by running this.
Ito's activation.
Oh.
This is Ito's activation.
Backward Eulers on
Yeah, it's
current.
personal.
Ito is lambda thing, right? Similar, but a bit different. And then what? And then like with denoising score matching, they are able to estimate the score. Just the score of the mixture of Gaussian at any points. And the difference is that they need to take the t into account. So the LT they have here is the conditional score conditional score
This
matching.
is the same as what we just.
Yeah,
saw.
yeah. Then to calculate this LT, they can just use a single sample. What does this mean? To calculate the LT, we can just use a single sample, the Monte Carlo estimate.
One simple,
It's SGD.
one simple estimate, one simple approximation of the electric.
Oh, I see. Yeah.
One.
So basically at one point you just only sample one x1 and then only sample another xt from this condition and then calculate the loss term. So eventually if you do it for many times, it will
Yeah.
closer to the
And then it's still the same as before.
It's just it's kind of like if we had our mini batch, we would do this per mini batch or something.
Yeah, it's just SGD.
Like,
You can sample several in one training step.
even for one, I mean like there's an inner expectation also. So for that also we don't do. I mean like for one it's not in
So
I think
this
we
sample
don't do-
one, this sample one.
Yeah, this is also second one is also one I think.
Yeah.
Ideally we should do multiple, but only one while we
Convert just faster or something. Yeah. Cool.
that T will only be one, right? Because this is LT theta. So
What is one?
the inner expectation we will be doing only once, right?
Yeah, only one sample.
no, but ideally we should do many, right?
It's
The
all,
XT is still random variable.
I think it's just for implementation.
Exactly.
Why can't we only use like small?
What?
This is just estimating the two excitations using mini batch or using multi-con. Right?
Yeah. So it's
What is
just
is there
SGD.
like any specific statement that only using like a single sample is enough for this? Like, what is the point? of this?
No, you can. It's like you can have lots of samples and train it one by one.
Yeah, but what does it mean that we can use a single sample? It's always an estimation. Right?
That's like why you can do SGD. You are sampling from data distribution. Why are you only sampling one?
Yeah, so I'm confused about this sentence. Is there anything special about this function that it's like they only use one single sample or there's
No, there's nothing.
okay.
It's just the joint distribution of X0 and XT.
Yeah, so how can you estimate one like the two expectations using only one sample?
No, they're saying having one sample here, one sample here.
It's a very rough estimate.
Yeah, but over time, not time as in this time, but as you keep training, it doesn't matter, right? Like you can do this multiple times, or you can update after each sample also.
Like you draw one X naught and then repeat, keep that X naught fixed and draw many XPs at
Then,
different
then,
times.
I mean, this wording is weird, right? Then it says
Could be bad
LT.
writing. Because it says, yeah, LP.
Yeah, we don't know if this sample means a data sample or like we're talking about XTs, different XTs.
I think that's just
I
empirical,
think this is some
Weird
weird
wording.
language, yeah.
not too important. I think. So in figure, this is just a visualization. Well, then they talk about an example of the score generator model, variance exploding probability flow SD, ODE. So basically they are currently, I think they are defining a specific FG, and in given this, they are able to derive this. So in various exploding SDE, in the original score diffusion paper, they are assuming the drift term is 0. So in DDPM, you basically shrink the data at each diffusion step and then add noise. So here it's saying that it's not shrink the data and directly add noise. So the variance is exploding. And this is how they control the sigma schedule. And then according to the discussion above, yeah, they plug in it here. So the ODE, the flow ODE becomes something like this.
I don't know how they got this conditional, they're saying it's derived based on how an SD is defined, right? So,
Oh, you're saying this?
no, the next one,
Oh, this one?
yeah.
Oh, this one, I don't know. They're just saying that from the theory, from this book, they tells you like given X0.
Is this Ito's integral? Because if we took the expression before, right, and instead of P of xt, it's actually P of xt given x0. And if we integrate it, would we get this? Like, is that the,
I think so.
but that's solving SD. No,
What?
I mean, oh,
It's Markov chain from 0 to t.
yeah.
Given X0, what's the probability of xt? I think, like for example, in DDPM, they are able to derive it because it's just summation of Gaussians.
Right.
And the integral, they have something similar. And the integration of this formula, the integration of this could result in this.
That is just the solution of the ODE itself, right? If we could do that,
Yeah.
then we wouldn't be using Euler's method. I think this is not using that,
Oh, it's not. This is not derived using this. I think
right?
this is derived using the SD using this, right?
Yeah.
But if you solve all these things, they don't give you the distribution. They only
Yeah. So you solve this because you know the forward. It will give you the distribution. And somehow in the score case, they are also able to getting this, and then the variance over time is the following.
So is this like we calculate what that sigma will be at each x0 to say x delta that we move? We calculate that sigma, and then that's it, right? Like that, then then it will be a Gaussian distribution.
Yeah. So
I ideally want, so if you solve that, the equation, you
So the equation is dt dxt is just equal to sigma t d phi t, right? So this is the
Yeah.
forward process, right?
The drift is 0.
And then what it's
what is
doing,
the equation? What did you write? I didn't ask. What did you write there?
this is a SDE. So they are saying that gt is sigma t to the t, and fxt is 0, and I'm just substituting into here.
Oh, right.
And then this is what they have, and then they are saying like xt, so pxt given x0 should just be no idea. Huh? How to do this?
Check that chapter 5.
The appendix of Psalm 2020.
What will not come?
That has some Jacobian and those kind of stuff, huh?
If you
Yes,
direct,
we can just assume we can have this closed form solution.
if you substitute the dvt as the normal, you get the first formula in your screen. dxt over dt.
Can we just assume that xt is x0 plus sigma t dt?
DBT, right?
What is what if it's dbt? How are you taking the inter what?
DBT, DT or DBT?
I don't think there's a
dvt is
DT in the
normal
border.
times dt, right? dvt is normal times dt.
If it is normal, it's an DT. So how do we integrate this?
dvt is what?
The normal distribution times dt.
Yeah. Error dt. And this is even stochastic, huh? This is n01. And yeah, I
Oh,
think
it's no, it's not the absolute dt, right? This is dt.
what?
Because your Wiener process
Yeah,
has
the standard deviation.
standard deviation is related to dt.
The DD is not outside.
dt is somewhere in here.
Yeah.
And then if you expand the epsilon out, you have dt in your standard
That's
deviation.
exactly the same, right? You multiply by dt, then your variance becomes dt.
It's not that simple.
Oh, that's also true. Yeah, that's true.
So here, this dt is deterministic. Just random thing becomes epsilon. Just
That's true.
But even if you solve this, how do you go to the distribution? Ex given x.
So ideally, so I was hoping it will come some x equals to x naught plus
no. If you
some noise term.
if you think about the discrete case, it's x0.
Given x naught, it will become a Gaussian with a mean x naught plus some weird variance. That's what the form is, right here.
Yeah.
Exactly the form here. That's what I was hoping. So basically, it should be something like x equals to x naught plus this
That
variance
variance.
term plus some epsilon. Square root of variance this term plus epsilon. That's what it should come.
If we do not have this sigma t, this is totally solvable, right? If we do not have this sigma t, so sigma to the t is equal to 1, then this is totally solvable, right? It's just a Gaussian with variance t, right?
Variance t,
Yeah.
The song paper also says we should look at equations 5.5 and 5.51 in that Solin 2019.
Everything traces back there.
Reference chain.
Yeah, given an SDE equation, they derive the probability at a particular time instant, starting from. Yeah, yeah.
They have stochastic integral there. And then, yeah, so they have this distribution from 0 to 1.
Since the norm will come from the sigma from that's the K power X.
No, log
Goes up, right?
1 by x representation is log x.
What about the general exponential 2 power X? So what are the-
Where's Romet?
Oh, I see.
Yeah, it is.
Yeah,
So that log comes from.
yeah.
But how does it go to the denominator?
Where's Romet? He should come, right? He said he should come at 1, right?
Yeah. What is it then?
150.
145.
I think what's left is not important. What? What?
So, what from here will like, we understand still have
This
those
is not
things.
close at all. We have not touched close.
I suppose the next one.
But I feel like it's just the rehashing of all this. We are pretty much just doing, so from this we get an idea like if you had one distribution on one end, like either T1 or T0, whatever, we want to, that is Gaussian, right, usually. So we are assuming one side is noise and then we're jumping in steps iteratively so that the end is the data distribution. Pretty much that's what we're washing and repeating in all this.
Put an end now.
No, if you want to understand flow matching, this blogs will only tell you, okay, like this is they have shown, so this is true, right? So this matches. That's what I got.
Okay, so the way the probability distribution is derived is by Fokker-Planck Kolmogorov equation. You write that we
Planck equation.
yeah,
Planck.
Fokker-Planck and I thought only those two, but it seems that Kolmogorov is there in
Yeah,
everything. He's doing everything.
So are we in a position to read a flow matching paper now?
I think so.
Yeah, definitely.
Next time we can.
Next time.
Next time I mean next time probably. So last time I mean like in the blog they mentioned some results, right? Because from the original score matching to conditional flow matching, they say it's
Equivalent,
equivalent,
yeah.
but the proof is given in the paper. Alright, that's what this is.
Yeah.
I think you should be able to understand given that if we assume that particular SDO the systems are true.
Yeah.
This one is like 3 lines of equation.
Why is Romet? Someone go and get Romet. Oh. Okay. That's it.
Yeah, I grabbed Anna and go to the shop together. And the boss was like the white guy who can speak Chinese fluently. It's not fluently, and he just can't stop talking about his Chinese accent. What?
Yeah.
Is it the
Six,
word
six, and one.
chair?
Sitting and more.
Sitting and more.
Yeah, sitting and more.
Did you tell that you are doing UIUC, CST or something? Yeah. You didn't say anything.